So our next speaker is Tom, who will be telling us about semi-analytical models of spiral planet wakes.
So good morning, everyone. My name's Tom. I'm a first-year PhD student. I started last week, so I don't have too many exciting new results from my PhD to share, but instead I'm going to talk about some stuff that I did during undergrad on semi-analytic models of spiral planet weights and some applications. So here I have a phantom simulation of a planet tidally interacting with the disk and exciting a spiral wake, which I'm sure many of you have seen before. But I'd like to motivate the rest of my talk by asking, well, why is it that we should get this? I guess it seems somewhat natural that the planet should excite waves and those waves should interfere, but at least I find it surprising that you get actually such like a coherent structure that seems to live in the disk. So I want to start off by doing some experiment where instead of putting a whole planet potential into a simulation, we break up the planet potential into Fourier components. And so here I'm showing a plot where I have the star in the middle and then the planets at x equals 1. And I've decomposed the potential of the planet into the first 9 Fourier components in azimuth. So you have this m equals 0 mode, m equals 1, m equals 2. And so this is the form of the decomposition where you have some amplitude that depends on radius and then the azimuthally varying part. So if you stick this into a hydro simulation instead of having a whole planet potential and you run a separate simulation for each one, what you find is that you get different spiral structure depending on which component you have. So if you take the m equals 2 Fourier component, so this one, and you stick that into a simulation, you excite a double arm spiral. And if you take the m equals 3 one, you excite a triple arm spiral, etc. And so that seems kind of obvious because you're driving perturbations in the disk on just this like twice per orbit or 3 times per orbit sort of thing. So then if you add these up afterwards, you find that actually they all interfere in a specific way. And so in each of these, you have this n equals 0 arm, which is centered on the planet location, basically. And those ones all constructively interfere, while all the other ones destructively interfere, and they sort of go away, and you're just left with the wake centered on the planet location. This is a nice video made by Jay Hanbei. So the first thing I want to talk about is the theoretical framework for understanding the shape of that spiral. And so to understand this, the first thing we need is the linear disk response from a small perturbation. So basically, if you take the 2D fluid equations for a disk and you add a small perturbation, you end up with the dispersion relation shown here, first derived by Lin and Xu in 1964, which basically tells you how your waves will travel through your disk for different modes M, where it's an azimuthal wave number as before. And then so once we have that, we also need to think about how the planet tidally forces the particles in the disk. And so basically, if you take a test particle and you add the potential from the star and from the planet, you get a Lagrangian like this, where you have the orbital kinetic energy of the test particle and then the potential. So then if you do some expansion to second order and you add the form of the potential in terms of the Fourier components, you come up with this second order ODE, which is just a simple harmonic oscillator on the left, but then it's driven. And so the variable is the radial perturbation of the orbit. So it's basically telling you how it forces eccentricity. And so you have on the driving term on the right, you have this function that basically tells you how hard it's being driven, and then the time. And so if you solve this, I mean, it's very simple. It's just a harmonic oscillator. You end up with this term on the bottom that actually can go to 0. And so if that goes to 0, then the perturbation basically explodes. And so this is the condition for a resonance in the disk. And it's basically for each mode, the location in the disk, which is most effectively excited by that Fourier component, I guess. And so these are called Lindblad resonances. And basically, if you just take the condition, you can derive the radii in the disk that are most effectively excited for each mode. And that's what I've shown here. So this is a plot basically of all the radii in the disk, the planets at 1, and then all of the resonant locations. And so for the m=2 mode, these are the locations in the disk that excite the spiral arm. And then as you go to higher and higher order modes, they stack up nearby the planet. Yeah, and so once we have this and we have the dispersion relation, you can calculate basically the position of the spirals for each mode in the disk by considering lines of constant phase. And so what I have here is phi is the angle of the position in the disk where the wave is for each different mode. And so there's 2 parts. There's this offset, which is basically where azimuthally the wave is launched, and then also this traveling term. So the offset is kind of complicated where you get it from. I don't really get it. So, but it ultimately comes from the behavior of the area function. And so this basically tells you, it looks complicated, but it's just where in the disk your wave starts. And then you have this propagation term, which is just taking the dispersion relation from before and integrating it. And so that doesn't look too exciting, but what it lets you do is actually calculate the shape of each spiral, each mode separately in the disk. And so here I'm showing the m=3 mode, which is the 3-arm spiral, which is excited by the 3rd Fourier component. And so these 2 rings show you the Lindblad resonance positions for that mode, where the wave is excited and then it travels in and out of the disk. So the planet's here, the star would be here. And each one of these colored lines is like one of the spiral arms. And so the thing that's interesting about this is if sort of we continue our line of reasoning from before and you take the mode that's closest, like the arm that's closest to the planet, and then you go to large values of m, they all stack up on top of each other, which is probably what we expect from before. So basically take the limit for large m and you take the n=0 arm, which is the one centered on the planet, and you get an analytic prescription for the shape of the spiral wake. And this was first derived by Ogilvy and Lebeau in 2002, although their reasoning was a little bit different. And so this is how you get the shape of the wake in general, but then we need to, I guess for what we wanted to do, we need the density perturbations and the velocity perturbations. And so that brings me to the semi-analytic calculation of those things. And this is what most of my project was focused on doing. So the details are a bit nasty, but basically you separate the problem into part nearby the planet, where you consider the problem to be basically linear if the planet's small enough, and then a part further away from the planet. So we take a Cartesian box centered on the planet, and we use this local approximation that a couple other people have shown in their talk. It's like the shearing sheet. And we solve for each separate Fourier mode of the perturbation. The equations are terrible. And then you do a Fourier transform back to real space. And so you see that this is where the planet would be, and then this is the wake that's excited. So this is the radial velocity component. And then so once you've generated your wake nearby the planet, we take the edge of the box as an initial condition, and then we solve for the nonlinear behavior as the wave steepens and forms a shock eventually. And so you can show that actually to solve this, it's equivalent to solving a one-dimensional Burger's equation, which is reasonably simple, but getting here is not simple. So you basically take, you use the fact that we know the shape of the spiral arm from before, and you do a clever coordinate transformation where you basically get rid of the shape of the spiral, where you have a pseudo time coordinate along the wake and then a space coordinate across the wake. And then that lets you reduce it to this form. So this is just a simple PDE that we integrate with a finite volume scheme. And so once you do all that, you get something very pretty that looks sort of like the simulation. So here's the planet, and then the linear part of the solution's in here, and then the nonlinear part's out here where it steepens into a shock wave. And so this is a density plot. And then also this is what the velocity components look like. So we have, this is the radial velocity component, and then this is the azimuthal velocity component. And the location of the box is much more obvious in these plots because we have some issues with connecting the velocity between the two regions. So a lot of my work was developing a Python package for doing this in a fast and efficient way. And we also improved the accuracy of the method a little bit. So this is work that I did in collaboration with Daniele Fasano and Francesco. And so some of the improvements that we have are like we have adaptive time stepping for solving the PDE and lots of efficiency improvements. And so one thing in particular that we did was we improved the accuracy of the extraction of the velocity. So I have more nasty equations, but basically the way that we calculate the velocity is we take a locally isothermal equation of state and we just use the equation of state to relate the difference in density to the difference in sound speed. And previously this was done to first order originally. So they basically, you take your equation of state and do an expansion to first order and then throw out all the higher order terms. And then that lets you relate the sound speed to the density. But I actually noticed last year that there's no real reason to expand it unless you just like really like taking expansions. You can just invert it and keep all the higher order terms. And so that's what we did. And so this fixed somewhat our problem with the velocities not matching inside and outside the linear and nonlinear regimes. So these are plots centered on the planet location. The top is the radial velocity component. The bottom is the azimuthal velocity component. And on the left is the old method, which was first order in the sound speed. And now on the right, I'm showing the version that keeps all of the terms. And so the match in the velocity over the edge of the box is quite improved for the radial and then not really indifferent for the azimuthal. So now I'll just briefly discuss some applications that we've done with this stuff. So primarily we're concerned with disk kinematics and trying to use this to measure planets by the disturbance that they make in velocity channels. So here's the kink in HD 163, originally found by Christoph. And so there's this deviation from this smooth profile that you would expect from purely Keplerian rotation. So this is like a slice in velocity of the total disk. And so in some work we did with Josh Calcino, we showed that these deviations are actually found all throughout the disk, and they can be perfectly explained by a planet wake, basically crossing the channel. So here's an analytic model that I've made, and this is to try and demonstrate basically that you have red shifted material here and blue shifted material here, which corresponds to a crossing of the wake. And then you have the same thing down here. It's kind of hard to see on the projector. So if you make a peak velocity map, which is basically taking the flattening all the velocity channels into one image and taking the highest velocity for each pixel, you get a map of the kinematics in the whole disk. And we found that there's actually these spatially correlated wiggles, similar to the GI wiggle that Cristiano talked about, and that we can fit this with a planet wake pretty well. So especially in this bottom region, there's these little wiggles that basically correlate with the wake location. And we also made an analytic model that pretty much agrees with this and replicates the wiggles, and also a phantom model. We also applied this to a disk HD169142, or disk around HD169142, in some work that we did with Himanshi. So she basically subtracted a best fitting Keplerian rotation to the disk and found this big kinematic arc here, and we wanted to see whether we could use wake flow and MCFOS together to replicate this feature using a planet wake. The answer seems to be that we can't really. And this turned out probably to be because the disk is very face on, and so the motions are likely mostly vertical, and the 2D analytic theory can't account for vertical motions. So some other possible applications of these semi-analytic models is to actually build a statistical tool that takes kinematic observations and performs proper fitting instead of like the modeling that we've done so far. And so our collaborator, Daniele Fasano, is actually working on incorporating wake flow into the statistical tool disk miner to try and do this, to actually measure planet masses from the kinematics. Another possible use is just cheap parameter space exploration before running your expensive hydrodynamical models. And yeah, possibly any other ideas that you might have. So yeah, that basically brings me to the end of my talk. Thanks so much for listening.
Thanks, Tom, for the great talk. Does anyone have any questions?
Hi, thanks for the talk. I was wondering, is it possible to extend this somehow to 3D? Like, because you showed that you have two coordinates.
Yeah.
Do you think, because presumably you would increase the temperature as you move upwards,
Yeah,
but you would
yeah.
also decrease the density?
Yeah.
And I was wondering if you have any insight on this, which effect will dominate? Probably the sound speed, so the temperature?
Yeah. So there's some theoretical work on this, looking at especially like how the dispersion relation would change with 3D. The answer seems to be that it's pretty unclear, because it's the neat stacking of all the modes into a coherent structure kind of fails, because you can't throw out the azimuthal wave mode dependence in the same way. So it's pretty unclear how you would try and do it analytically. It's something that I tried to look at a bit last year, because definitely, like, I mean, we're measuring kinematics from like a few scale heights, so it's definitely going to be important, and vertical motions will be important. But it's pretty unclear how to do it with the analytics.
But the good thing is that your analytical model, when you try to fit the channels, you get like good results in there. So does this
mostly
mean that the vertical extent is not that important in the end, or does this mean that we are slightly shifted to the real answer?
So for a real 3D disk, work by, I think, Steve Lubo shows that if it is truly vertically isothermal or very close, the modes are exactly as they are in 2D. So if that's the case, then the vertical stuff is probably not very important. It's actually that in that case, they're the same as surface waves in the ocean, basically. And so we can probably trust the 2D stuff if we're close to isothermal. And especially if the region that we're probing doesn't have temperature too different to the midplane. So I guess it really is a question of how vertically stratified disks actually are.
Another stupid question is, what would happen if you have an eccentric planet? Is that something?
Yeah, so people have done that.
Be done with wake flow?
So you can't do it with wake flow right now, because it's calculating a solution that's completely independent of time. But recently, I think last year, the theory was extended to account for planets on eccentric orbits. So it's something that you can do. I don't know the details, but as far as I know, it's essentially the same principle. You solve for all the modes and add them up. It's a bit more difficult to do it for in the eccentric case, because you have to do it globally for the whole disk. You can't do this shearing sheet box thing. And when you try to do that in practice, it's hard to solve for. You kind of have to throw out problematic modes by hand and stuff.
Okay, thanks. And you can put several planets, I assume, right? Like you can put 2 planets in Wakeflow. Or...
you can't put it in Wakeflow, but I could make it so you could put it in Wakeflow if you would like to make an issue on my GitHub.
Thank you very much.
Does anyone else have any questions? Let's thank Tom again.